Welcome folks, a video today on eigenvalues and eigenvectors. So we'll define what an eigenvalue and an eigenvector of a matrix are. We'll see a few examples of vectors and values that are eigenvectors and eigenvalues. We'll talk about how to find them, and then we'll do a few examples. Okay, so here's the definition. Suppose that A is a square matrix. Square matrices may have eigenvectors. X is an eigenvector of a square matrix A with eigenvalue lambda if A times the vector X equals lambda times the vector X. So oftentimes we call this the eigenvalue-eigenvector relationship. This is pretty easy to check. Just compute A times the vector X and see what you get. One of the keys to this is that our eigenvectors are non-trivial, right? The vector X must be a non-zero vector. Okay, so here's an example. Let's have a look at this matrix A, this vector X. It turns out that A times X is 4 minus 4, 8, 20. It's pretty quick to see that 4 minus 4, 8, 20 is 4 times the vector X. So we say that A has eigenvector X with eigenvalue 4. Okay, here's another one. It turns out that that this vector y has A times y equals the 0 vector. Okay, so this doesn't immediately remind you perhaps of an eigenvalue, but certainly A times y is 0 times y. We say that A has eigenvector y with eigenvalue 0. Here's another one for you to play with. So I'll ask you to go ahead and verify that that A has eigenvector X. It turns out with eigenvalue 2. And similarly, that A has eigenvector W with eigenvalue 2. Okay, you might be asking whether A has other eigenvectors, and it turns out it does. For instance, you could try the vector u equals 30 times x. If we try u equals 30x, you should find that A times u is A times 30x, which is 30 times ax. Of course, we know that ax equals 4x. That's the eigenvalue-eigenvector relationship for x and 4. Now, of course, we can reassociate that scalar multiplication to see that AU is equal to 4U. Similarly, if we try V equals Z plus W, we see that V is an eigenvector corresponding to eigenvalue 2. Of course, since Z plus W is exactly V, we see that AV is 2V, and that, like I said, V is an eigenvector corresponding to eigenvalue 2. So we see sort of an interesting relationship here. Any scalar multiple of an eigenvector is an eigenvector, and any sum of an eigenvector is an eigenvector. We'll explore that more in a minute. So let's talk about how to find these eigenvectors and eigenvalues. In the previous example, I gave you a matrix and gave you some eigenvectors, but it turns out that we can find them. Here's the definition of the characteristic polynomial of a matrix. Given a matrix that's square, the characteristic polynomial P sub A of x is the determinant of that matrix minus x times the identity matrix. Okay, so this is reasonably easy to compute, right? You just go ahead and write down A minus some scalar times the identity matrix, and then compute its determinant, right? So we know how to do that. So here's an example that I'll have you explore a little bit on the worksheet. For this matrix F, let's go ahead and find the characteristic polynomial. So here's the matrix F minus x times the identity matrix. Of course, that just amounts to subtracting x from the diagonal. Now, there are all sorts of tricks to the trade here, but when we go to find the determinant of that new matrix, we should find that it simplifies relatively quickly to something useful. So when it comes to eigenvalues and eigenvectors, there's no right or wrong way to simplify determinants, but I noticed that we could get a couple zeros here by adding -2 row 2 plus row 3, and then taking row 2 plus row 1 to give us a new row 3 and row 1. Now, once we do that, we can introduce one more zero by taking negative column 1 plus column 2. So we've now introduced a row of zeros across the top, well, almost a row of zeros, and we should be able to find that the characteristic polynomial, the determinant of f minus xi, simplifies pretty quickly in this case. And here's what you should get. You should get the quantity x plus 1 squared times x minus 3 times a minus 1. So you'll notice that this characteristic polynomial of a 3 by 3 matrix is a cubic, and it turns out that a characteristic polynomial of a size n matrix is always a size n polynomial. So here's the theorem. Suppose that A is a square matrix. Lambda is an eigenvalue of A if and only if the characteristic polynomial evaluates to 0. Okay, and the proof of this theorem is based on the definition of eigenvalue, namely that lambda is an eigenvalue if ax equals lambda x for some lambda, some x rather, that's not 0. So here's the chain of equivalencies. Lambda is an eigenvalue if ax equals lambda x, if and only if ax equals lambda times I times x. Now, of course, we can manipulate this equation to rewrite it as a minus lambda I x equal to 0. Okay, of course, this says that x is a non-trivial solution of a homogeneous linear system, which can only be true if the coefficient matrix A minus lambda I is singular. Of course, we know singular if and only if the determinant of that matrix is 0. And in this case, we've just defined the determinant of that matrix to be the characteristic polynomial evaluated at lambda. So here's the take-home message. If we have a square matrix of size n and you want to find the eigenvalues, first find the characteristic polynomial, p sub a of x, then find the roots of that characteristic polynomial. So solve p sub a of x equal to 0. Okay, so we just saw this matrix, and hopefully you found that the characteristic polynomial here. So given that characteristic polynomial, we should be able to find the eigenvalues. Since the characteristic polynomial is a quantity minus quantity x plus 1 squared times x minus 3, the eigenvalues are lambda equals -1 and lambda equals 3. Okay, so we saw that solving for eigenvalues involves solving a homogeneous system. That might remind you a little bit of a subspace. Here's a definition. Suppose that A is a square matrix and lambda is an eigenvalue. Then, by definition, the set of all eigenvalues for lambda together with the 0 vector is called the eigenspace for A. And here's our notation. We write this as epsilon sub A of lambda. Okay, so here we can write this, also express this in set notation, sort of a convenient way. So quite simply, given A and lambda, the eigenspace, E sub A of lambda, is the set of all V, such that AV equals lambda V. Now, I want to point out that this eigenspace explicitly includes the 0 vector, right? Whereas the 0 vector is not an eigenvector, but the 0 vector does satisfy this relationship, so we include it in the eigenspace also. Okay, having called this a space, you might not be surprised to hear that epsilon sub A of lambda is a subspace. In order to show that it's a subspace, we'll just show that it's non-empty, closed under vector addition and scalar multiplication. So of course, by definition, the zero vector is an element of the eigenspace, so it's non-empty. If V and W are elements of the eigenspace, then their sum is 2, so we see that it's closed under vector addition. And if alpha is a scalar, then alpha V is also an element of the eigenspace, so we see it's closed under scalar multiplication. Okay, the eigenspace is a subspace. As almost a really quick corollary to this theorem, we can definitely see that that the eigenspace can be rewritten as the null space. A vector V is in the eigenspace of A corresponding to eigenvalue lambda if and only if AV minus lambda V is 0, if and only if A minus lambda IV is 0 vector. Of course, solving such a homogeneous linear system is the same as finding an element of the null space. Okay, so this is cool. Given an eigenvalue of a matrix, an eigenvector is an element of a certain null space. Okay, so this is a good thing, right? Because we know how to find null spaces of matrices, and we know how to write them as spans of linearly independent vectors. So that's what we'll do for eigenspaces also. We'll characterize them the same way we characterize them as null spaces. So here's an example that I'll have you work through a little bit on the worksheet. We saw that this matrix F has eigenvalues lambda equals 3 and lambda equals -1. So if we want to figure out the eigenspace corresponding to eigenvalue 3, all we have to do is compute the corresponding null space. Okay, so I'll have you go through this on the worksheet. You can compute F minus 3i, reduce it to its reduced row echelon form. The way we've cooked up this eigenvalue 3, there must be a non-trivial solution, and what you end up finding is that you can express that eigenspace as the span of a set of vectors containing one vector. Okay, so I'll let you work through the details on that, but you should find that the eigenspace of F corresponding to eigenvalue 3 is the span of a set of vectors containing the single vector -1, 1, 2. Okay, similarly for lambda equals -1. And again, I won't take all the fun away from you, but when you have a look at the null space of F minus -1 times I, you should find that that null space can be represented by the span of the set of vectors containing two vectors, and those two vectors are -1, 0, 3 and -2, 3, 0. Okay, so again, finding these eigenspaces is a problem that we know how to solve, right? Because we know how to characterize a null space. Okay, something interesting you'll notice here is that being linearly independent, the dimension of this eigenspace is 2, and it turns out that's an important characteristic of an eigenspace. So we'll talk about a few more examples where we dive a little bit deeper into this dimension. So we'll start with a couple of definitions. Here's the first definition, the definition of algebraic multiplicity. Alpha sub A of lambda, the algebraic multiplicity of lambda corresponding to some matrix A, is the highest power of x minus lambda that divides a characteristic polynomial. So just as an example, for this matrix F, we saw that the characteristic polynomial can be written as minus times the quantity x plus 1 squared times the quantity x minus 3. And we can see pretty quickly that the highest power of x plus 1 is 2, so the algebraic multiplicity is 2. And we can see pretty quickly that the highest power of x minus 3 is 1, so the algebraic multiplicity there is 1. Now, on the other hand, the dimension of the eigenspace tells us the geometric multiplicity. Okay, since the dimension of the eigenspace of f corresponding to the eigenvalue -1 is 2, we say that the geometric multiplicity of f corresponding to the eigenvalue -1 is 2. And similarly, since the dimension of the eigenspace of f corresponding to the eigenvalue 3 is 1, we say that that geometric multiplicity is 1. I had a little typo up here before. Sorry about that. These should be sub f, not sub a like I had them before. In any case, those are the algebraic, alpha for algebraic multiplicities of eigenvalues of the matrix F, and geometric, gamma for geometric multiplicities of the eigenvalues of the matrix F. Okay, you'll notice that in this case, the algebraic and geometric multiplicities are the same, but as it turns out, that's not always true. Okay, so here's an example where we can compute the characteristic polynomial of this 4x4 matrix to be x minus 1 times the quantity x minus 2 squared. We can see pretty quickly from the characteristic polynomial what the algebraic multiplicities are. Okay, again here, since there's an implied 1 power, we see that the algebraic multiplicity of the eigenvalue 1 is 1, and similarly the algebraic multiplicity of the eigenvalue 2 turns out to be 3. So we can also compute the geometric multiplicities by having a look at the eigenspace. Okay, so I won't go through all the details, but if you want to look at the eigenspace of the matrix B corresponding to the eigenvalue 1, have a look at the matrix B minus 1 times I. Right, of course, we're going to find the null space, and we can see that there's exactly one free variable here, so then the dimension of that null space is 1. Since the reduced row echelon form of that matrix B minus I shows one free variable in the corresponding homogeneous linear system, we know that the geometric multiplicity, gamma sub B, corresponding to the eigenvalue 1 is 1. Okay, similarly here we can see that the dimension of the null space of the matrix B minus 2I is also 1. Okay, and again here the new wrinkle is that the geometric multiplicity of this eigenvalue 2 of the matrix B, the dimension of the corresponding null space, is 1 in this case. Okay, I'll have you sort of run through a similar example on the worksheet for this matrix, matrix C. It has eigenvalues 3, 1, and minus 1, and the algebraic multiplicities of those eigenvalues we can read right off as 1, 2, and 1. Okay, again, those algebraic multiplicities correspond to the power on the characteristic polynomial. On the other hand, when you go to have a look at the geometric multiplicities, we can see that the dimension of the eigenspace here is 1. This tells us the geometric multiplicity of the eigenvalue 3 is 1. Okay, again, the dimension of the null space of the matrix C minus 3I tells us the dimension of that eigenspace, which is the geometric multiplicity of the eigenvalue. Okay, similarly here, we see that the geometric multiplicity is 2. In this case, I think it's instructive to show that the eigenspace of C corresponding to the eigenvalue 1, not 2, 1, is the span of the set of these two linearly independent vectors, and it turns out they're orthogonal. That's kind of a cool deal that we'll explore a little bit more later. Okay, one more example here, and it's pretty quick to show that the eigenspace corresponding to this matrix C and eigenvalue 1 ends up being of dimension 1 also. Okay, just sort of to summarize this example, we found that this matrix C has 3 eigenvalues, including multiplicity, one of those eigenvalues, 3, has an algebraic multiplicity 1 and a geometric multiplicity 1. One of those eigenvalues, 1, has algebraic multiplicity 2 and geometric multiplicity 2. And the third eigenvalue, -1, has algebraic multiplicity 1 and geometric multiplicity 1 also. Okay, it turns out that having matching algebraic multiplicities and geometric multiplicities is a good thing. It makes our life a little bit easier. I'll let you go ahead and work through this example, but it turns out that the algebraic multiplicity of the eigenvalue 2 is 4. The algebraic multiplicity of the eigenvalue -1 is 1. Of course, it turns out that the geometric multiplicity of the eigenvalue 2 is 2, and that the geometric multiplicity of the eigenvalue -1 is 1. Okay, so we'll explore those algebraic and geometric multiplicities and their relationships in our next section when we talk about properties of eigenvalues and eigenvectors. Okay, folks, a lot here. I hope you've enjoyed learning about how to compute eigenvalues and eigenvectors and how to describe them in terms of their algebraic multiplicity, which is the highest power of a factor in the characteristic polynomial, and their geometric multiplicity, which is the dimension of the corresponding eigenspace. Have a great day. We'll talk to you soon. So long for now. Bye-bye.